Hi, so this is Travis Baker,
And this is Stefan Lofgren.
and this is our presentation on our 4-bit processor. So here, first of all, we wanted to start off giving you an overview of the whole design. We're going to take it piece by piece and explain to you what each of these blocks does, and then you'll see the final result at the end. So we're going to start with the binary counter. The binary counter has a clock input. It has 8 bits of output, so it counts from 0 to 255. And it progresses by 1 on each clock press. So it's just a simple up counter. It sends the 8-bit output to the PROM.
And then those 8 bits come to our program PROM here depicted in this diagram, which which the program PROM has about 10 functions that you can program into it. No operation, some things to move some data around, some ANDing or adding, and exclusive ORing of bitwise pieces. Each of these values are written in binary as shown, but as they get coded into the PROM, they're stored in 2-bit hex numbers. And so you'll see really quickly here that the 4 upper bits, those bits go to the instruction decoder, which tell the processor how to work, and the lower 4 bits are the data that gets loaded into the mux and then into the register file, as you'll see here. Our PROM, or our ROM, is a 128 by 8, which allows for up to 128 lines of commands, which gives us a variety of things that we can use to accomplish all the tasks that we need to with this PROM and this CPU.
So now we have our instruction decoder, and this takes the 4 bits, the upper 4 bits from the PROM, and puts out 8. There's 8 different outputs that go to different parts of the overall design, and this is on the screen here. This chart shows basically what the inputs are and what the hex input is, and this is what determines what it's going to do. And like Stefan said, there's a total of 10 commands there, and this is the output that it gives. So with each hex code or binary code as seen on the left, the output is what's given on the right. So for each of those pins, that's what's given. And there's an option of having a subtract pin. That's really up to the consumer for us, but for us we just chose for that to be a switch since it was one simple bit.
Okay, so next we'll describe real quickly what the data mux does. The data mux takes in 4 bits from the PROM and 4 bits from the ALU accumulator, the register file in the accumulator, and then it also takes one selector bit from the decoder. And based on the input, it passes the information it gets from the PROM or the ALU into the register file to be stored or used in whatever the context you'll want to use it in.
And our register file is just a simple 2-register, it has 2 registers, so it's a 2-word 4-bit register file. It takes in 7 inputs, a clock input that's synchronized with the rest of the system, a write enable, and an address bit which come from the decoder and determine where to write the 4-bit input word that's sitting there from the data mux. And it has an 8-bit output. It outputs both of the data from the registers. And that goes to the ALU and the ASCII display.
So real quickly, the sum of this whole project kind of comes down to the ALU and what you can do with the ALU. The ALU, and we've added the accumulator as well to be able to store the functions or the results of our functions we've used. The operation has 4 operations, and you can see on the screen the table shows you how the selector input bits choose which choice you'll want. So there's 8 bits that come from the register file, and those are our 2 words stored from the register file, and we can add them, or them, and them, or exclusive or them together to get some of these results. And we've also additionally added in a function through a subswitch to be able to handle subtraction, thereby enabling us to do signed binary numbers as well as unsigned. So by default it's unsigned, but if the subswitch is asserted as high, then we can handle signed numbers as well using 2's complement, which helps us to kind of wrap up and finalize our processes through the CPU. Again, this is kind of what the whole thing looks like. We have on the left-hand side, we have the 4 functions, as well as it kind of all jumbles into an ALU mux, and then that goes to the results of that get sent to our 4-bit register. And the ALU mux really is just a bitwise 4-to-1 mux that gets pulled, whereas it chooses the function you want for each bit and handles them separately. And we've tried to organize the ALU mux diagram so that's native and makes sense and follows that kind of pattern. And then this is quickly our altered adder circuit. We essentially put in some exclusive ORs to be able to handle subtraction. And this is seen here as those exclusive ORs. And those handle with the B inputs, and that's where it's triggered. So the second word that gets sent in, or B, A would be stored in register 0 and B would be stored in register 1, and that kind of determines where we want. So if you want to deal with signed numbers, put them in the second register.
And last, our ASCII display real quick before we get to a demonstration. It takes in an 8-bit ASCII character. The upper 4 bits come from register 0 on the register file, and the lower 4 bits come from register 1. And that outputs it to the LCD display on the Xilinx board. And this is the finished schematic with everything wired up. And next we'll show you a quick video of our demonstration. And that is the end of our presentation.
Thank you.